Hello guys, welcome back to another episode of this series. We are trying to write our kernel from scratch. Last time we started work on our architecture-specific interrupt items, but we still have a few issues with those. So today we are going to finish the work needed to make those run fine and try to see our interrupt handlers get called back. Then maybe start work on our kernel-specific interrupt handling internals. So let's get started. Oh, right. So it wouldn't be a Falcon Code video if I don't start by talking about changes that were made off recording. So a few fixes went into making this GT entries work. First of all, before in this limit here, we had max uint of U16 for some reason. So that had to be changed because limit is a U20. Global descriptor, there we go. So limit is a U20, and we just initialized the 16 lower bits of that, so that's bad. Now, there's also this default size here, and is 64 bits, which we did not really interpret correctly. So this one is 64. So before it was just named a 64-bit, but in the manual they basically say that this one indicates if this entry here is for 64-bit code specifically. So for data entries, we had to set that to false. Same for default size. They basically said, so this is a classic reading skill issue where we just did not read the damn thing. So this flag here, the default size should be always set to 1 for 32-bit code and data segments, and otherwise for 64-bit code segments, it should be set to 0. And for 16 bits also. So that's something else that I had to do here. So I went through and made those changes and everything worked out fine. I also made a few changes here. So instead of just having this GDT here call init, and in the init we do the load GDTR. That does not work because for GDTR, we are loading the address of our, so where does it go? There we go. So we load the address of the GDTR struct that we've created there, except that since here we are returning in this create function, we are returning a self, so it gets copied basically. The location moves, so we cannot just load whatever we create here on this stack. So that's that. Same for flush, same for IDT, except that IDT now does not load its IDTR. Instead, the interrupt subsystem does the load after it sets all the gates. Yeah, and it enables interrupts. So that's that. Also, I think in GDT, I also have printed these values here, just bitcast them to U64 and printed them out. And the reason for that is I want to compare them to known values. And the known values I got from so kernel, GitHub, I guess we could go there. And so under architecture, x86 boot, and I think it's a compressed it's 64, and somewhere down here, there we go. So somewhere down here we have the values that they expect for their kernel code segment and kernel data segment. and that's how I validated that my values were correct. So that's pretty much how it went. Yeah, so today I want to finish at the initialization by adding the TSS. So here under max TSS, I think we need to put max CPUs, and I'll have one per CPU. So here I need const. Hold on a second. I think I've put this here. No, these are architecture specific constants. So the constants I'm looking for are these ones that are under the constants module. So constants is import constants. There we go. And here we can just go ahead and do constants dot max CPU. There we go. So here we'll have one TSS per CPU, just so that we can have them do switching on their own, task switching that is. Cool. So now we need to get rid of this descriptor 16 bytes. I'll just call it for now task segment descriptor. Sure, it doesn't hurt. Right, so now let's go down to here, and this is where we are going to make our change. So we call that task state segment. I forget. Very cool. So let's go. We don't need this anymore. We now need this guy to tell us about TSS in 64-bit mode. Cool. So we have a 16 bits of segment limit, and we have 24 of base. Let's start with those. So limit lower, I think. Do we have a upper limit? We do. U16. Then we have base lower is U24. Let's keep track of how big this should be. So this one is a backstruct of a U127, no, 128. Right, so here we have type, and what is this type here? Type is 3 bits. And I guess type is the same type that we have. Yeah, segment type is basically. So it's the same type. Segment type, sure. And how is that? 4 bits. Is that how much we have? Yeah, okay, so 8 and 11 are included, so 4 bits, yeah. Fine. And then we have a unused 12th bit at 0 always. So let's call it unused 0, sure. This one is a U1 and it's always at 0. And then we have the privilege level. I think we have, so privilege is how we call those, privilege level. And I think we should probably give it a default value. There we go. Segment type here, I'd like it to be fed. Lower and base, I'd like them to be fed, so that's fine. Right, so now privilege is ring 0. P is the present bit, present as a boolean, I think. And let's call it false for now. Then we have the upper 4 bits of limit. Sure, so that brings us to 20 bits. So limit upper 2 Ps, please. U4, sure. Then we have so unused one, just a U1, set that to 0. And then we have 2 more zeros. So let's, this one I'll call AVL, just in case. So unused 1 is a U2. And then we have a granularity bit. So how do we call this? I guess we call it this, right? So let me just copy that. Oops. Very nice. Okay. Granularity bit, and then we have the rest of the base. So how big is that? I think that's 8 bits plus 31 bits. 32 bits. Right, so base, upper, and that's U40, I think. Should be about right. And then we have a fully zeroed out U32 up top. Yeah, sure. So unused, I guess, 2. That's a U32, and that should be just set to 0. Cool. Now let's just get this here, just so that it can serve as a template. We're gonna get rid of this. We're gonna get rid of that. We know we'd like to get a base, which would be, so how big is our base? We have 64, U64. So that's a U64, then we'll have a limit. Our limit is 16 plus 4, so U20. Right, so let's first of all dupe these, go over here, do change offset to base everywhere. And here we'd like to, so the first base is 24 bits, and the upper base is 40 bits. Yeah. So args.base, args.base, and this one here is U24. Sure. Let me try something here. Type of at field field, I can type. So it takes the thing. Yeah, but we need to refer to so let's try this task segment, and the field is called base lower dot int, I think dot bits. Yeah, we need to close that parentheses there. What are we missing? So this one is matched. This one is matched. Okay, so there's one extra there. All right, we'll try this to do, make sure this is fine. If this works, I'll probably package this into a helper function or something and use that everywhere. The reason we want to use this is so that we do not mess up doing the computation here, if instead of U24 I write in U20 or something, it's going to be bad, and it's going to be hard to find out how bad it is. Right, so here we go, args.limit. Same goes for this one, and this one I'll just leave it as is. Of course, this one here, offset should become limit. Sure. And these go, and here we go, limit lower is limit lower base lower is base lower, and then type is args.type, which we should go and get. So this one is segment type. So I'm thinking about this. I think we can default it to something insane. We should probably be able to create a TSS. So I guess kernel TSS type segment type dot create with something. We need to read up on what needs to go in that. Sure. But is that really the type we want to get, though? Because there's this type here, which is segment type, and there's descriptor type. And let me just reread. So this one is segment type. Because I guess descriptor type is this bit here, and we've set that to 0, so it's fixed as a system type. Cool. Right. So that's that. Now let's go next. Privilege is I guess we could leave that to be ring 0, right? Not sure what we did for the other ones. Yeah, we put them into our thing here, but we did not use them. So privilege is privilege level, and that's a default to ring 0. And we just set that here. Privilege is args.privilege. Cool. Then we have the present bit. And this I'll just set to true, because if we've created, that means we want it to be used. So then limit upper is limit upper. And then we have granularity, which would be I guess args.granularity, but that should also be defaulted. Sure, something like this. And then base upper, which is just base upper, I think. Yeah. So that should do it, I think. I think that's all right. So if we go back to GDT now, so let's think about this for a bit. Okay, so these are the entries. Let's now take this and do something like TSS entries. And this will go from that, right, to, so I'm thinking, so let's do a double slicing here. So we go from that to the end, and then we go from that start to so size of segment dot task segment descriptor times max TSS entries. Does that look okay? I think it does. It's not too bad. And here we need this to be task segment descriptor. Yeah, okay. So in line 4, and we want this to go from 0 to constants.max CPU. We can do better, I think. Max TSS entries. We get that as TSS index. Sure. And we move. So now we need to figure out how we are going to set these. Right, so all of these don't really work for us. Those are 32-bit specific things. What we want is instead to know how the TSS will link to our task segment thing. Rather, how our TSS descriptor links to our actual TSS, which is this struct here, which we still haven't created yet, by the way. But I think in base, we should put the address of this struct here, and limit would be this size -1. These are TSS entries. Let's call this TSD entries, so task segment descriptor entries, just so that, sure. Let's rename this to be max TSD entries. Cool. So now we need to go for each one of those. So for TSD entries of, I guess we should call this TSD index, right? So TSD index. And this would need to be, so create. And I guess we should pass it the struct. So base would be, well, here we need to define, I guess, some sort of TSS. We need to define some sort of TSS entries, of TSD index. I guess something like this, and then limit would need to be. So this one we can just copy from wherever we create our GDTR. Speaking of which, sure. So this one would be size of, yeah, sure. I think the closest thing to this would be this one here, right? Yeah, so we just need to go size of thing, size of, I guess, segment dot task state. Is that? Yeah. Yes, yes, yes. So size of task state -1 would be the limit. And what else do we need to pass this? Can I get segments, please? Yes, thank you. So limit, then we have type. And this type here would like to have it as segment dot, I guess, kernel TSS type. Sure. Privilege we don't really care about. We can leave it as it is. Sure, that looks fairly okay. Now we need to define two things. First of all, the TSS type here. So we are going to need to figure out segment types, segment registers. So segment type, is it defined somewhere here? Sure. Okay. All right, system descriptor types. TSS, sure, that's what we like to have. So 64-bit TSS, we want this and this, so 8 and 11. So accessed and code. Sure, that's fairly easy. So accessed is true and code is true. Is that all we need? And what's bit 9? Should we mark this as busy? For now, I won't do that, and we'll see if we are wrong. And actually, now that I think about this, can we just simplify this and just create? It's a fixed value, right? It's just a 9. Yeah, I think that would be better to do that. Right, so this type here, let's go down, down, down. So let me just go ahead and create a const. Pubconst, I guess, type is enum of u4. So how do we go about that? Yeah, so we'll just put in values. Let's do invalid, which would be 0. Does 0 have, I think, reserved? Cool. And then we can do TSS available. Sure, that would be 9. And then TSS busy would be 64. Busy is 11. There we go. Cool. So, of course, we need to get rid of these. Nice. And here under type, we can just take type now. Type. And of course, now we can just do TSS available as the type. And yeah. So we can go here and remove that. Cool, very nice. A bit of cleanup here is needed so that now we can have our task state. Cool. Now, this would probably need to go. So public function fill gtr self void, and I'm just going to split this to here. Okay, public function fill tss self pointer to self does return nothing, and we are going to get this to here. The reason for that is we need to do this. And so we are going to need to go up here and do TSS entries. Again, entries. And this would be so size of let's go TSS entries. If I can type that, size. Sure, const. I guess we could now just do this. TSS entries size is size of segment.taskState times max TSD entries. That is okay. And that means that here we have segment.taskState. I guess they should naturally line. I didn't see anything about alignment requirements. But yeah, anyway. And I guess we should just zero initialize them, right? Let's think about this. Yeah, it's not a bad idea, I think. Sure, segment.taskState state. And this would be mem.zeros. So it needs a type, which is segment.taskState, which we need to also correct over here. Cool. And this would go for max TSD entries. What is the problem here? Oh, right, of course. These are field definitions. Nice. So this one goes here. And this one goes here. So now we have that set. We just need to do put self here in front of every one of these. Okay, and here we need to put self in front of this also. That looks okay. Now we also need to inline for so 0 to max TSD entries. I think we could have left that to be TSS. Just saying. Right, and here we should go ahead and initialize the TSS entries themselves. So TSS entries at TSD index. So they're all set to 0, I think. Yeah. And if I go somewhere around here, TSS descriptors in 64-bit mode. Yeah, sure. And is there anything here that we need to know? So we need to do this load task register operation to load the TSS segment descriptor. But for now, let's move task segment descriptor. That's fine. We don't really need to have any of those. Task switching, this does not apply to us at all. Right, so here we go. 16-bit map from TSS base. These ones we don't really care about. This one here, we need to create IST tables. So we need to allocate physical pages and map them to serve as stacks for interrupts. As for the rest, I think we just need to set the IO map base address to something that basically points away from this struct here. All right, so let's do that. Right, so we'll set IST 1, I guess, to be some sort of stack. And I guess we could do something stack of TSD index because we'd like each CPU to have its own interrupt handling stacks, so we can do interrupts load balancing afterwards and have the freest CPU handle the interrupts whenever possible. And here we can go ahead and do TSS entries TSD index.io map offset, and let's just set this to sure, set math max int of U16. Sure, why not? Now we need to know about this stack thing here, and for that I'm going to need to go back to yeah, so I'm tempted to do something like this, to just basically create a huge undefined or zero initialized BSS segment. So let's see how we did that. Oh, so we just marked them as heap and we marked them as no load here. Sure. Otherwise, we would like, or we would have to allocate the page and then map it. But we still don't have the facilities for that. We have a physical, we can do it manually. We can get physical pages and then map them to a range of our choice, but this would likely be changed in the near future. So I'm not going to do this just yet. What I am going to do though is take stacks, which would be a max TSD entries, U8, no, so this times arc.constants.page size, or default page size. I think I've renamed that default page size. So now I need arc, which is just import arc. Yeah. So this one is, or maybe I should just split them. If I do something like this and just have that be there. So it's an array of TSD entries for which each entry is a page of U8. So if I go stacks, and of course, yeah, sure. Probably should take a pointer to that. Actually, I could make this a slice, which would make a pointer by default, but I want the constraint on the size. All right, let's leave it at this and see if it works as a pointer or it's copied somehow. I doubt that, but okay, that's fine. I think I understand what I'm trying to say. Right, so this one here would need to have the address of that. Yeah. Sure. Okay. Now let's go to this. Do they talk about interrupt stack tables anywhere here? Probably in interrupt handling, interrupt. Stack switching, interrupt stack table. So motivation for ISD, blah blah blah, is to always know execute on a known good stack. That's fine. Okay, sure. Shadow stack, we don't really have that. Okay. So we are good to go, I think. Right, so now the only thing that remains is to load. Oops, let's do this and go over here and do public fn load tr with self void and do that. Sure. Sure. tr, and this would need to be right. So let's first of all write this. So volatile, and I guess I'll use the multi-line string thing. So LTR, I think. This here needs to be do we have sure. No, we don't care about those. So 9, chapter 9, task management. Sure. Okay. I just want to know what the load TR. I guess sure. That's that should be easier. Okay. All right, that's fine. If it's not for an available TSS, then we general production. If it's not present, then okay, we not present. And otherwise, we set it to busy. And then we write the hidden registers. Okay, cool. So the LTR instruction is provided for use by system software. That's fine. What does it take? It takes a register or memory, 16-bit memory value. I think we are going to go through a register. So it's 16 bits fixed. And I think that's just enough for us to fit a... yeah, that's fine. So I guess TSS, how do we call that? Selector? Sure. So no inputs are TSS, selector, if I can do that, and then we get that as a register, and its value would be, I think we are going to have a bit of difficulty here. So let me just get this this hacky thing I did for for the data segment and code segment selectors, and have that here. So now that we have this, we need to know which one we want to load, because we have a few of those, right? We have one per CPU. Yeah, one per CPU. So we are going to need to know which one to load. So I'm not sure if we have this anywhere, but let's CPU ID. Yeah, so we've introduced this notion of CPU ID for lock-in. So let's do that. I think we should probably define this type here as an architecture thing, because depending on the architecture, the number of CPUs that can be addressed will change. Sure. Otherwise, let's keep going, I guess. So here we took the segment, but here we just want to calculate it given the... So I think we don't really need to do any of these things here. And this one would be TSS selector. Sure, this goes to, and now this one here would become so segment dot selector, sure, and I think so what are the things that need to be put in this? I guess just the index, right? So index is, and now here we need to figure out the, so we know that we have max GDT entries is 5, so that's the index we are going to start from. Where were we? There we go. So max GDT entries plus CPU ID. But that should put us over the limit of what this can encode, which is a U13. So truncate to U13. How do we go about this? Sure. For what am I doing? CPU ID. Sure. And this one be TSS selector. Okay. So what's the problem here? Known result. Well, as U13, that, there we go. What is the problem here? Self is unused. Sure. Whoops. Maybe do something like TSS selector. no, we don't have a formatter for that, so just do that, and here we can do self. Sure, okay, that looks fair. Right, so let's get to the rest of this. Here we need to do, first of all, gdt.fill gdtr, as we've split that off now. And then gdt.fill tss, except that this now takes a stacks parameter, so stacks. And that means that here we need to create stacks, which would be a arc max constants, sure, max CPU thingy of a arc dot constants dot default page size of U8, which would be something like this of constants default page size. This will be hard to initialize, but okay. And for each of those we need of U8, of course, here. For each of those we need this of U8 at 0 times arc constants default page size and this gets timed by arc constants max CPU. Right, I can do this. So const arc is import arc. Right, so what is the problem here? So const, I guess it should be a var. It's not public, but we'll declare it for now. The only problem I have with this here is now we are, I think we would be inflating the binary size for our kernel for absolutely no reason. Yeah, we'll see. Okay, so gdt.load tr, and then we flush the gdt, and yeah, that would be okay, I think. Now let's go to our dispatcher here. So before we had our a logger, I tried to log something. I've changed that to this panic message here, just in case. But what I'd like to also add is ASM volatile and just do a hold instruction on our CPU. What is the problem here? Unreachable code. Sure. Okay, fine. That's okay. Let's build this and see how broken it is. Unable to load file. Under arc. Is that because I need to cd kernel and sig build gen arc? Why is this not working? So let me just remove that and regenerate it. Okay, so maybe that's a problem with the generation, or oh, I think I know what the problem is. So let me just remove the cache. Sure, and now it should just work. Yeah, that was it. So let's go back, rebuild this, and now we are okay. So in descriptors, whoops, this one here, in here, constants has no member max CPU. Oh, so that's not, yeah, that's not under arc. That's under constants. Import constants. Sure. So that's under arc. But that's under constants. Okay. So GDT, GDT. What line is that? 20. Expected type. Okay. Found 8. Hold on. This one is a... Oh. Bad. Very bad. TSD entries. Yeah, the size is already encoded into those. So do we use this anywhere though? Okay, so it does. You go. Expected type U64, so that's in 75. That's fine. I think we could cheat a bit here by going to types and so for all of these we did have a is it worth cheating here? I guess we could just, yeah, for all these we had fixed values. For the IDT, I think we had a pointer, an actual pointer here. Yeah. So I guess we could do the same for this, or int from pointer. Let's not get too distracted here. So types address of operator always returns a pointer. Expected U64 found pointer in, so here. Int from pointer of that. Now, member function expected 1 argument found 0. Right. Sure. Let's think about this, sure. And let's set it to 0. Okay, so if I go here, go down here and do. Okay. So has no member base lower. Segment task, segment descriptor. What is this? Has no member base lower. Are you kidding me? Task segment descriptor. Okay. You know what? I'm done with that. I am done with that. So let's go type info of U24, I think, .bits. I'll look into that afterwards. So destination type is has more bits than the source. Of course, here we haven't touched any of those. Okay. Okay, it did build. Now, is it going to run? That's the question. Right, so here I'm just going to add no shutdown, just in case. Okay, cool. Not really, but it seems like we have bigger problems. How come? Where does this fail? It fails about here. CPU info. Okay. Let's try something else here. Let's do debug interrupts. And see. So we get an interrupt. So E is, I believe, a page fault. And the faulty page is this one here. Now I would like to do something else here. Read L/A build kernel, sure, accept that, into kernel dump.txt, sure. And let's get kernel dump.txt here. And I just want to see what goes to this region here. Oops, there we go. This region here. So it should be fine. I don't think there's anything we write explicitly there. There's the stack we set at 0 for our kernel. Otherwise, I don't think there's anything else. I'm also looking for the symbol, the stacks we have created. So let's see, where are the stacks? Stacks. So I guess they are not defined here. Yeah, not defined here. Okay, so let's try something else. Let's try removing this and this. So this should bring us to pretty much how we should be before the TSS changes, and we can infer from that if we broken something. Yeah, it's running fine. It is running okay. Well, we still do get, hold on, let me just remove the interrupt stuff. Yeah, so we create the ISR interrupt vectors thingies, which should be called from here. In gen interrupt, create an ISR for vector. Sure. Okay. I guess we could get rid of that. And we will be just fine. Okay, so we have something that's broken in our code somewhere. Right, so let me first of all go to here. Go to here, remove this, rebuild in debug mode, and rerun this, but this time with the changes, at least these ones, here. In debug mode, we go a bit further, but we still crash before we get into the descriptor. Okay, so let's redo this. I'm interested in knowing where it put things. So if I stacks, there we go. So this stacks here got put directly onto this here. And if I go to take a look at here, so 6.9 is BSS. So stacks should be correctly put into BSS. So what is the problem then? Let's put back the debug interrupts, just see if it's going to fail, and it does fail for more or less the same reason. We are trying to read from an unmapped page. And actually, let me just take a look at main. Sure. Oh, right. Okay. That's actually fine because we have put this code here, which triggers an exception. Although the address is not really the same as we expected, but let's see. Sure. Yeah, I think we are crashing before we get to that. Whoops. I think we are crashing somewhere in descriptor.init. And I think I should do something like this. One error. What is the error? yeah, sure, that's not really how it should go. Okay. Okay, so this fill TSS is the problem. Now, TSD entries is this, and here we are using self.tss entries, which I guess would be these here. Right. Okay, so let's add a few debug log things. So debug, and here we'd like to know, so TSD entries, we want the pointer to that. I guess we should do something like this. And we do TSD entries here. And then here we'd like to know, TSS entries. And this would be self.tss entries. I can type that. Okay. Fine. Right, so we do crash before we get to this. Which leads me to believe that somewhere here we have something that's not great. What is the problem here? So this scripter is we create it. That should be fine. We fill the GDTR. That should also be okay. And then we fill the TSS, and I guess we should also try to debug log the stacks. I guess we could do something like this. Stacks. Okay, this is sure, no shutdown. Just wait for a debugger to be attached. We want to build kernel 64.elf, and we want to break on descriptors .init. Okay, so the thing we want to keep in mind is the address on which we failed, which would be something like, so if we go back here, if we have history, we should be able to see the address on which we failed. There we go. So it's somewhere around here. So 7F8 with everything else is FFFs. And actually something that we need to check is this is the instruction we executed. So let's do an op dump -d -mintel for build kernel 64 elf and put that in kernel dump.txt. Right, let's go. Open kernel dump.txt. And we should go to, so hopefully I've copied the value. Okay. So where is this? udiv mod t. Huh. That's okay, that's not really what we were looking for. Let's see. Yeah, there we go. So 59E74. So somewhere here. Let's see, what was our stack like? Or what were our registers like? So RSI was here. And I think, so this is a division somewhere. Okay, right, fine. Let's go to our debugger and we find out. So next. Right, so that's fine. Fill GTR, I think I feel like that's safe. Yeah, it does look safe. So let's print stacks. Descriptor dot stacks. No, stacks. Okay, that's fine. So we'll step into fill TSS and we'll do info locals and info args. Optimized out. Okay. But let's see here. Descriptor stacks is passed in RDX. So can we do this descriptors stacks? All right, that's fine. So let's next. Okay, so this is where we fail. At least we know. At least we know. So what did we mess up? I think it should be something as easy as just looking at this, but let me go ahead and set this to undefined. Okay. No, never mind. Let me just compute something first. We have set a max CPU of 8. So we should get 8 pages. So that's 8 times. So that's 32,768. And if I take a look at read elf-a kernel 64.elf, of course in build, kernel 64.elf, and we go for, let's look for stacks. It's the correct size, so that's fine. That is correctly sized. Now, let's go to here. This is what's scary about this. So we want bytes as slice will try to do a division. And it should be exact, as in this size here should be the exact size of these structs here. Now, the question is, do we actually have those? Wait, hold on. What is this max TSD? This should still be 8, and this GDT entries size plus the task descriptor, segment descriptor times the number of entries. So that's so far so good, I think. This is for something else. This is for the task state segments, or just task state. And so what is the problem here? Let's split this off. So const, let's call this TSS or TSD entries buffer, and that I'll set to self.gdt entries buffer from size of segment.global descriptor times max GDT entries to the end, basically. Sure. And that means that this would be TSD entries buffer. Okay. And I think without even having to do this, slicing here, it should still give me the correct values. So if I go ahead and do this, TSD entries buffer, TSD entries buffer, sure, and let's rerun this without the debugger this time. Probably we need to rebuild this first. Sure. Let's see. No, still have a problem. And if we also do something like GT entries buffer, and we go for self.gdt entries buffer, are we going to see anything change? No, still nothing. And I think we have two problems. First of all, the log is not flushing, at least not often enough. Let's see if we can just fix that quickly. I don't want to spend too much time on this. Writer.flush, new interface.flush. Does this fail? It can fail. Sure, let's build this and rerun this just to see. Okay. Okay, so it was not a flushing issue then. Cool. Very nice. We don't have anything from this. Let's add debug logs here. Loading GDTR or filling. Of course, this needs a second argument. Okay, so it's not a flushing issue, it's just most definitely something to do with this. Right, let me just remove this for now, move it down here. Huh. Okay, so we do have a fill for this. Oops. But as soon as we get to this call here, something bad happens. Just going to should not have initializers. I still do have do want to have initializers though. No, export I think is what I'm looking for. Let's just try to make it a bit more visible. Okay, cool, fine. So dash S, capital S. There we go. Info breakpoints, which should still be fine for those. Continue. Right, so e locals, no locals, print stacks has a known type. Let's call it okay, and let's go for 1,000. Sure. Okay. Kind of weird, but okay. So that's the address of stacks. And now if we go next, again, and then we step into this, we should expect to have optimized out, but the value that we get passed here in RDX is 6B580, which is the value we expect for that. So that's okay. Now, what are we doing here? So we are in move here. We are going to call zig probe stack. Oh, I think I see what the problem might be. Yeah, okay. So let's go here. Next instruction. Okay, well, next instruction again. And here we land in this probe, stack probe. I think we have landed in Zig's stack production code because we, I think we should not do this. We should probably do this and go here and do a pointer to that, whatever that is, so that it doesn't think that we are trying to pass that in the stack, and it should not try to protect us from overflowing the stack, basically. Yeah. Let's retry this again, of course. All right, let's go again. So info breakpoint, that should be still fine. And let's go. I think this time I'm just going to also add a breakpoint directly to gt.fill. So this script doors.gt.fill TSS. Sure. And let's continue to there. Okay. So let's take a look at the assembly again. So this time here we don't have any call to zigzag protection, because this time we have told it to explicitly pass this as this argument as a pointer. So that's fine. Right. So if I go now and print stacks. Yeah, I'm not sure about that though. Let's print no, that's not really what we wanted to do, but if I take the first value of stacks, what does it have? Yeah, something is not tracking. Something is not tracking here. I think we messed things up. We took one more pointer than what we should have. So let's think about this. Right. No, this should still remain that, but this should be this. Yeah, okay. Okay. So does that mean that I need to do this? Because this is a pointer, but now this is a mini item pointer instead of just being a slice. And that means that here I should get a slice, and the slice itself should be just a small stack widget that has a pointer and a length. And so here I'm just gonna mark this as a to-do, check slice length. Okay, now let's stop this, rebuild this probably. Sure, let's just run this without the debugger. Okay, so that now does track. maybe I'm not going to print those. Maybe I'm not going to print those either. So going to need this up here. Right, let's rebuild this. All right, so what's this thing printing? Nice. What is the wall of zeros? Stacks. Stacks. Oh, right. So let's get rid of those. Okay. And hopefully we can have something we can think about. Right. So TSD entries is that at FAED8 FAED8 that does not look good. TSS entries. Right. So this one is a slice, so let's just print it as a slice then. No, let's just get its pointer. Yeah. So that's how we are going to be able to tell. This pointer here, TSS entries, and this pointer here should be fairly close by in memory. And yeah, indeed they are. Yeah, that's very promising. Very promising indeed. So here I'm just going to get the interrupt. Just want to take a look at something. Right, so let's actually go back to our main and put back our code here. Wow. Okay, so not good. Not great. That's probably sure. That should create an interrupt, right? Okay. Probably not. Probably not. All right, let's get rid of that. Sure. Okay. So I'm taking a look at these values here. They look okay. So these are values for our GDT and IDT things. So GDT, we have our data segment here, here, and here. And we have our code segment in CS, which is a 64-bit code segment. Our TR, I'm not sure about this. It does not look great. So let me just go ahead and try to debug that. Just the the TR loading, basically. First of all, let's do this, see that we do get TR loading. Did we enable? Okay, we did not. All right, that explains some things. All right, let's see. Okay, now let's put back our exception in there. I guess this should be enough to create an exception. I'm trying to be quick about this. There we go. Great. Great, great, great. So now we have a page fault exception here because we tried to access something here. Init interrupt. Cool. And would you look at that? Our TR is now correctly loaded. This is our own. We can recognize it because Xerox28 has index 5 in there. So if I do calculator and we go hex 28, then here we have the number. Okay, so now we actually do have the TRs loaded correctly. Now the only problem we have is this exception here. We need to check where this exception comes from. So I'm going to just do a opstamp. Sure, let's accept this. And if I go to kernel.txt, we should be fairly easily find the instruction here that causes the problem. And let's just zoom into this and see here where we are. What is this function? Hopefully this is the failable main. Cool. And this instruction here is just after the descriptors in it. Yeah, sure. So it's the actual instruction that caused our problem. The only problem I have with this is where is our current RIP? We're still at where the exception happened. We have not been redirected to our interrupt handlers. Okay, so that's something we need to take a look at next. Yeah, so this is where the exception happened. Right, so now why haven't we been redirected to our interrupt handlers? So here we initialize this, we load the IDT. Let's check the IDT here. It looks all right. Let me just go ahead and probably just go to GDT to load GDT and take this and put it here. This one needs a log, so const log is log scoped for IDT. So IDTR, and this one needs to be IDTR, not base. Oh, right. Let's, oops, really what we wanted to do, but okay. Sure, let's go. Just want to check that our IDTR is, yeah, that's not really what I wanted to print though. And it's set to 0 for some reason. Oh yeah, because I haven't. Fine. Okay. Right, let's see here. So 73000 and 73000. That's fine. So the actual IDT that's currently loaded is our own IDTR. That is okay. Now, so here I just want to check what is the 0xC. So exceptions 0xC, so ABC, stack segment fault. Uh-oh. Okay. So let's see here. We have a stack segmentation fault. And we have no error code, or rather the error code is 0. And that should mean that we have a stack segment fault somewhere. So here 74000 is somewhere in our IDT registers, I think. Okay. Let's see how our things are getting set. So I want to go to interrupts, and in here, no, that's fine. I want to go to this create. So we are saying that the IC should be 1, and that we are trying to load the kernel code segment selector. Let's, for just 1 second, put this IC to 0. Oops, sorry. Go on. And let's see here. Okay. All right, so this time we don't have the stack segment thingy. But we do have quite a few, not that many actually, exceptions here. And 0x6, what would that be? Invalid opcode, I think. All right, okay. So the invalid opcode, I have a feeling, is coming from, so let's just do this. Let's go to kernel dump, and I have a feeling this is coming from our interrupt handler, just panicking. And there we go. So that is indeed coming from a panic. Now, we have no idea what this panic is, but I think we can infer that it is coming from our interrupt handler. Yeah. Which means that along the way here, by setting the IC to 0, so asking the CPU to not do any stack switching, we have fixed our problem. And I think I might know what the problem was to start with, but for just 1 second, let me check. Here, so this is the same instruction in our main that's causing the problem. And so now, instead of having this be a panic, let's, for example, go to interrupt and replace this by, let's go for log debug and do sure, context. And here we are going to need to do volatile and just do a hold instruction. But we need to do the hold instruction for quite a while. Right. What is the problem? Expected bool. Right. Okay. Sorry. Not that kind of language, is it now? Right. Let's see. There we go. Right. So here we have a yeah, hold on 1 second. Right, so we still have the page fault. This time we have a 0xd, should be general protection. Yeah, okay. And I think the general protection is, or rather I think would be triggered by, so let's redo an op jump. Hopefully this is the one we want, yes. I think this one is triggered by the login code. So if I just look for this, is this a login function? It is a login function. Right, you know what? I'm just going to get rid of this. I just want to see that we do get into, right, fine, context. Do get into our handler. That's just what I want to know. And then we are, once we know that we are sure that we get into our handler, we can go ahead and think about fixing the other issues that we have. Right, so where are we currently? Okay, so we don't have that info, but we can actually have that just by doing this. All right, let's clear this and rerun GDB. Right, let's load our symbols file and break. Let's not break. Okay. So I guess now if I just interrupt this, and indeed I have interrupted the program, and we are in the halt within the dispatch interrupt. Cool. Very nice. So now let's talk about what the issues are. First of all, the main problem is, let me go back to interrupts. Where is in? All right, fine. There you go. Oh, we were there. Nice. Right, so that's not where I wanted to go. I wanted to go here, and I wanted to go here, and I wanted to set this to 1, to IST1. The reason for that is I do wanted to switch stacks. Now, the other thing is I want this. Where is it? This here, the fill TSS, to also fill the stacks correctly. So I've added quite a few log entries. So let's actually build this and see what we get here. So first thing I want to check is the entries themselves, I've printed them out, and I want to check if the values are actually correct. So first of all, let me bring up the Linux kernel's placeholder TSS. Right, so this is where we were before, and here they have a placeholder TSS, and we can see that it's zeros everywhere except here, where they have these 16 bits set, so to 1889, and there's no reason we should not have the same thing. So we have the correct types, the available flag, or rather the segment type set as TSS available, 64-bit, so that's fine. So we have 89. For the rest of this is the upper bits of the base, and these are the lower bits of the base. Actually, let me just zoom in here. Right, and we can see here the base for this entry for the first one is this one here. So 06B200, and here we have the Fs and the C, and here we have 06B2000. And then here we have 2 zeros, which are just part of the limit, or rather we have 16 bits, so 006F, which is the limit, which is the size of the TSS entry, and I think so 06F is 111, and we do -1, so that should be 112. Let's check the documentation. So we have 100 bytes, so +4, that should be hold on a minute. We have 100 bytes +4. So we should be at 104. Why are we at 1012? Okay, let's put a pin into this for now. Let's keep looking at the other things. So TSS entries, we have them starting here, and here for every TSS, I've printed the stack we've put into it. So here we can see that the stacks are spaced out by a page. I probably would like to have this aligned to a page. So let's start by doing that, I think. So that would be in descriptors and in stacks here. And I should probably go and align this to arc constants default page size. Sure. Let's rebuild this and see. Sure, let's just have it print out everything here. Let's zoom into this and let's take a look at this. Okay, cool. So now our stacks are page aligned, or page aligned, and that should make figure out what the problem is easier. So here we still have 0xC, which is the stack segment exception. So let's actually take a look at the size thingy here. We are expecting a size of 104, and we are getting a size of 112, I think. So this here would be wrong. So let's TSS size is let's get this as that, and then do size of segment dot task state. sure. All right, let's have that, and let's go again. Right, so 112. That's not good. Let me add something else. Bit size of segment dot task state state. Yeah, I should probably just add it to this. Sure. I'm just going to remove the interrupt debugging for now, just to get faster printing. Where is it? Where is it? Right, so 896 divided by 8. I don't know, bro. 896 divided by 8 is 1012. Okay, there's... Okay. Let's try this. If we force it to pack it. Where did I print that? 1012 still. But this time here, it's 823. So 832 divided by 8 is 104. All right. Okay. So that was the correct thing there. So the fact that we did not pack this, I think meant that some of these fields would need to be padded, and that means that we have our struct a bit off what it should have been. Right, so that explains why we did have issues. So now let's put back our interrupt debugging. Yeah, sure, I just want to put this back here and see if we actually still have the problem. And we don't have the problem. Hold on a second. We don't have the problem. What is our stack? Did our stack change? So hold on one sec. Stack segment, no, that's fine. Is it because we still haven't had a chance to print or do anything from our interrupt handler? Let's try this again. Hopefully this time we're not going to be let's see. Right, so we have quite a few of these. So these are general production. So can I just look for 0xe, please? Okay, and right after that, we get the general production thing. Okay. But this time, let's see here. Well, first of all, I can see that my stack segment has changed. So if we look at this, here we have CF093 and my God. So let's, no, I want to search up for 0x9, please. And here we have the stack segment has been cleared, set to 0, basically. And I think along the way, we should have our stack. So here we have our stack at C, so 06C. And if we scroll up, we have our, so did we not put the correct value of that? The first stack should be at 06D. So how come? Okay, right, so what the hell did we put into those stacks here? Yeah, that should be fine. Yeah, kind of weird. Okay, I actually would like to, before we make any changes here, let me just try something. Get rid of this. Let's tell it to wait for a debugger. And let me just gdb reset this. Target remote 134. Let's load file symbols from kernel 64.elf. And let's hardware break on what did we call this? Dispatch interrupt. Dispatch interrupt. Sure. Okay. Right, so let's see here. So I want to take a look at my stack. Yeah, I want, no, actually, hold on, 1 second. Let's print context. Yeah, sure, maybe. 0. That's not good. That is not what we expected this to be. So we've passed context. Hold on. Is the call convention not good? Because we have put, let's scroll up. We can't scroll up. Fine. Let's go here. So we've put, we've pushed RSP, popped that into RDI, and then we called dispatch interrupt with that in mind, right? So pushed RSP, put that into RDI, and then made a call. So RDI, so if I print, so as interrupt dot types dot context pointer RDI. Right, let's just do it the old-fashioned way. So let's print that as a car star RDI. Is it $RDI? Sure. And let's go for 128 of those. And I want that in hex, please. Right. So, what are we expecting here is at some point here we should see things we recognize, which are stack pointers and stuff like that. Right. No, actually, hold on. This is what we should be looking for. So all the things we put on the stack, basically. So all of these, ROX, RBX, RCX, all the way down here. So let's count them. So each one of these, we have 15 of those. Each one of those is 64 bits or 8 bytes. So that's 15 times 8. So that's 120 bytes. And then this one does not count, but what counts is the interrupt. Actually, let's just go for context. The size of context would be the tau, right? So this one here is, for this architecture, is 120 with all the registers. And to add to that, we add 1, 2, 3, 4, 5 times 8. So 5 times 8 plus 15 times 8. So that's 160. Right. 160 bytes. And if I open up my calculator and do 162 hex, that's 0xA0. Okay, so 0xA0. So how do we find where 0xA0 is? If we go back, so let's do 160 here. And actually, instead of this, I'm just going to do long. Sure. Yeah, okay, that's much better, I think. So let's see what we have here. Do we have any of these values still in their registers? No. No, we don't. So the very last thing we've pushed register-wise would be R15. But I don't see B0D3 anywhere. So maybe they got overwritten, but I see R11, 3F8. It's over here. I think I can see R10, which is 32, 0x20. 11 for R9, R8. Yeah, okay. And if we go the other way, so I guess 1B is, so X1B is 27. So okay, so this one is 12, R12, R13, R14, and R15. Right. Okay. So we actually do have our registers here. The only problem I see is, do we have them in the correct order? Yeah, R15 is the very last one we expect, or the very first one we expect, so that's correct. Okay, now that that's out of the way, so let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this would be the value of RBX. Did we mess up the... yeah, I think we have 16 registers, not 15. Yeah, I think I've messed up the computation. So let's do this again. So 5 times 8 plus 16 times 8. So 168 is what we are expecting here. 168. Yeah, but no. So 168 is in bytes and we want this to be in longs. So that would be 5 plus 16, so 21, I guess. Yeah. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And this is Rx, same value that we can see up here. And then this would be our vector. This would be our error code, maybe? Error code, yes. Then this is our RP. This one, 0x8, is what our CS, our code segment. And then here we have our flags. Okay, so cool. So in RDI, we do actually have our context. Now, there is just a small issue, which is why does dispatch interrupt not think that context is in RDI? Oh. Is it because we still have not moved? Right, let's go next instruction. So what do we have now in context? So print context. Ooh. So wait, what? Okay. That's weird, but at least that is the same value that we see in RDI. So now context does point to the correct thing. Okay, cool. Now, the other thing I want to know is why is our stack pointer not set to the stack we asked for? So it's basically set to just before RDI. So there was no stack switch. And does that mean that if we don't switch context, we don't switch stacks? In which case, that would be weird. So hold on a minute. Let's go back to this and let's add 22. So this here is our stack segment, or our stack before. Right, so if we go here, where is this thing? Okay. Task switching, that's fine. We don't care about that. No, it's not it. Yeah, okay. Stack usage with privilege level change. Yeah, well, they say unconditionally switches stacks when it is enabled. It can be enabled on individual interrupt vector basis by setting using a field in the IDT entry, which means okay, that's fine. The IST mechanism provides up to 7 IST pointers. In TSS, the pointers are referenced by an interrupt gate descriptor in the interrupt descriptor table. Yeah, okay, that's fine. Gate descriptor contains 3-bit IC index field provided and offset into the IC section. All right, we should be okay. When an interrupt occurs, the new SS selector is forced to null. That's something we see. And the SS selector's RPL field is now set to the CPL. That's okay. Also, we have that. We see that. The old are everything are pushed on the stack. Interrupt processing then proceeds as normal. If the IST index is 0, the modified legacy stack switching mechanism described above is used. Yeah, but our IST index is not set to 0. Okay. So how come? First of all, let's check that our IST is not set to 0. I think that's a perfectly normal thing to check. Yeah, it's not set to 0. Now, let's check the second thing. So we always set IST 1 for all of them. Right. This one here, IST provides blah, blah, blah. And then when an interrupt occurs, we set SS to null, we set the RPL to the current privilege level, and then we push all of these. Can be enabled or, yeah, that's fine. Oh, wait a minute. Let me put this back here. What we are setting is a stack, right? So, let me check something. So what we want to set here is a stack, right? So we have a bunch of stacks here, and we want to have them be used as a stack for our thingy. All right, here's how I'm going to do this. I'm going to simplify this by just multiplying this here, default arc page size. Just remove that. Let me zoom into here. Here we don't need to check any length or anything like that. We are going to need to slice these though. So DSD index times arc constants default page size to the end, and we take arc constants default page size from that. Sure. All right, let's keep going. I want to actually extract this to something here. So const, let's call this stack start address. Sure. But okay. I think I've got an idea here. Since it is a stack, that means that what we want, so this stack address here, all right. I think I've got this. Let me remove that. Okay. So what we want is, it's a stack, so it basically grows from higher addresses towards lower addresses, right? So we basically want to go, and the very first entry here would get the bottom of the yeah, I think it's easier to explain here in code. So I get the address. I actually get an int from pointer for the address of stacks. Sure. To that, I add the full size of stacks. Right, and then we remove from that TSD index times arc constant's default page size. So this stack address and this sure match. Let's change this to stack start address, and if I put stack start address here, I can remove that. All right, let's build this, please. Error. Yeah. Okay. Hold on 1 second. I need to go to descriptors here, and yeah, I'm just going to merge these two with a multiply. And I'm going to also merge constants.max CPU times that. No, just remove everything in there. Get a bunch of zeros and do that, and this would be arc constants default page size. Okay, let's try this now. All right, hopefully this does not kill us too much. Okay, let me just close this now. I'm looking for, let me zoom into this. I'm looking for where I've printed my stack. Whoops. No stacks for me, I think. Right, so where did we mess things up? Should surely be in GDT here. What's the last thing known to work? TSS entries. TSS entries and the pointer, and then what? Oh, TSS entries. Right. Okay, so this one here. And that means that something here is, yeah, okay. All right, let's retry this again. This time, hopefully, let's see. Right, I'm going to remove the things here. And okay, you can go now. TSS stack address. Let's see here. Okay, that looks very, very interesting now. So TSS stack address starts from. Do we have stacks? We print stacks. No stacks for you. Read elf. Yeah, just accept that. Please get me stacks. Stacks. Yes. So stacks starts at 6D. Damn it. There we go. So 6. Let's do calc. Right. So 6D000 plus what would be so basically 8 times rather plus 8 times 1000. Yeah, okay, cool. cool. So that's 75000, which is what we see here. And then that goes down, down, and down, all the way down to E000. Cool. Okay. That's good. Let's go back here. We set this to 1. That's fine. So what did we mess up here? Let's see. We want to go to interrupt, and we want to just remove this. No, we want to keep that there. But we want to rebuild this just in case we change something, and we want to debug this now. Because the reason why we were asking questions is we did not see our, or rather the stack value that we expected. So sure, continue. Okay, let's see. RSP, there we go. Would you look at that now? So it means that if we go next instruction, I believe, yeah, that's how the RDI is going to be, or rather context is going to be loaded. And if we go print context is in our stack. And if we try to deref that, it should be okay. Cool. So now let's do a quick computation here, just so that we make sure that it's fine. So 75000 minus a 0, which is the size of what we expect our context to be. That gives us f60. And we are very close to that. So that's here. And then we push 8 bytes. So let's remove 8 bytes from that. That's 58, which is this basically return from our call, because we call into dispatch interrupt. And then we I think this is the dispatch interrupt goal. Hold on. What else did we push onto the stack? So let's see here. From this value here, we loaded Rx with RSP plus 8. Oh, we still haven't done any of these, so yeah, I'm not sure why we'd want to count those in. So there's something weird here. Our current stack is at 4E18, but our RDI, which basically points to the stack where we landed. So the stack, when we get to here, should contain this call here will push its return address. Then it will push. Is it going to push the stack? Yeah, I think it's. Hold on, let me check if it pushes that. If at the end this function here does pops pop rx. Yeah, it's not doing any stack setup. It doesn't have the stack saving and loading thingies here. So yeah, I'm still not sure where we are, why we are so far from where we expect our stack to be. We are missing about 30 or so, 32 or so bytes, which is not huge, but now at least we can see that we have set up our stack correctly. Our speed does point to the stack that we've put into the IST. So that's very nice. So actually, never mind. I think I've miscalculated the things before, but if we do it again, so 75000 minus, so we have 22 fields that we push onto our stack, or that our CPU pushes into our stack times 8 bytes. So that brings us to F50, and then we call into dispatch interrupt, so that's minus 8 bytes more, which is the just push in the return value onto the stack, and that brings us to exactly where we would like to be. So 74F48. So we are actually doing great. There's no mystery anymore.